really excited to be here. This is my first time in New York, so it's really a lot to take in. My name is Laurynas Lubys, and today I'll be talking about how we are introducing a hermetic C++ toolchain at Uber. First of all, a couple of words about me. I'm a software engineer at Uber. I'm part of one of the infrastructure teams at Uber, and at the moment I'm working on evaluating / introducing ARM64 at Uber. I'm actually not part of one of the build-related teams. So I'm kind of our team doesn't own Bazel, so we're more of the client type people. Outside of work, I love music and play guitar and bass in a couple of small bands. So the agenda for this story, for this talk is really simple. This will just be a story of how we came to decide to introduce a hermetic toolchain, what issues we faced along the way, and how it's going. At the end of this, I hope that you'll be able to draw some lessons of your own. I won't be giving you anything prescriptive here. A couple words about the company. So it was started in 2010. Since then, over 15 billion trips have been made on the platform. We branched out to other areas such as food delivery and freight. We built a lot of cool and innovative technology to make it happen. Primarily, we use Go and Java. It's either a company-wide strategy or mandates, depending on how you see the world. I'm in infrastructure, and the vast majority of infrastructure is built on top of Golang. Rare exceptions do exist, but they are pretty rare. For example, we use C++ in some cases, but those are exceptions. We have a monorepo per language, and Golang is the biggest one. And the reason why we're talking about it is because that's the monorepo where we're introducing the hermetic toolchain and where most of my team's code lives. And that's what kind of we really care about at the moment. So let's get into the history. So Uber initially started using Golang without a monorepo. We had a lot of smallish independent micro-repos. The monorepo appeared in 2018. Go services started moving to the Go monorepo en masse. And that was a couple of years after Golang had been adopted. Our infrastructure services were one of the first to make the move. Once a couple of hundred services have been migrated in 2019, a ticket to set up a hermetic C++ toolchain for the Go monorepo was created internally, but it didn't get anywhere at the time. This is probably a good moment to refresh on what is hermeticity. Bazel box, well, that's a phrase we hear really a lot, but actually, just for this talk, I had to look up how Bazel defines hermeticity. So when given the same input source code and product configuration, a hermetic build system always returns the same output by isolating the build from changes to the host system. So the good thing is that the toolchain for Golang was hermetic from day one, meaning that the tools to compile Golang will get downloaded automatically, and you don't need to manually install a Go compiler to make it work. And regardless of where you actually build your code, it will use the same version of the toolchain. This is great for pure Go code. However, it will still use the C++ compiler found on the host in case you have Go code and C-Go code. And it turns out that quite a lot of code, at least in our cases, transitively depends on something that uses C-Go. And if there's any C-Go dependency in the dependency graph, your thing has to be linked with you need a C++ compiler and a C++ toolchain. Having an unhermetic C++ toolchain causes a lot of, not really problems, but inconveniences. The local compiler is unversioned unless you control the execution environment, but if you just have developers managing their own laptops, you get different versions of the toolchains. being used. So it's not easy to produce the exactly same artifacts that you get in production. And that means it's kind of, it might be more difficult to build a patched version of a production binary and test it out, for example, by deploying it on a server directly. The second issue that we kind of faced is that build machines must use an old glibc. So because if you're using the toolchain that's on the host, it will automatically, if it's a Linux host, it will automatically link to the glibc on the host, and glibc is backwards compatible, but not necessarily forwards compatible. That means if you build an artifact on a newer distribution, it might not work on an older distribution, and that means that CI machines are always the last to upgrade the operating system, and these glibc incompatibilities pop up at runtime, making changes in this area kind of scary. There are, of course, many more related to caching and things like that, but these are the ones that are most relevant to our team. Unfortunately, in 2019, the ecosystem for hermetic C++ compilers was not there, and it didn't really hurt enough for anyone on our side to really start investing serious time and resources into it. Fast forward 1 year. In March of 2020, Andrew Kelly, the creator of the Zig programming language, wrote a blog post where he announced ZigCC, a drop-in replacement for GCC and Clang. Amongst other features, it boasts a first-class support for cross-compilation, as well as support for linking against different versions of glibc, and it can even build macOS binaries. Additionally, it does all this without you having to manage a sysroot. So it has its own machineries to generate headers and stubs for glibc. Essentially, you can download a single smallish archive and use it to compile code for different architectures, operating systems, and different Linux distributions. This makes it a very compelling candidate as a hermetic C++ compiler for Bazel, because, well, you don't need a separate toolchain for every target that you have. Fortunately, it's not enough to just have a compiler. We also need the piece of glue to stick it all together. And it actually took another year for that piece of glue to come along. In April, Adam Buhengal creates a proof of concept Bazel integration. It's downloading LLVM toolchain for the AR tool, as it's still missing in Zig at this point, but it can compile basic C and C++ code with Bazel. Somewhere around this time, my colleague Mateusz Jakštis discovers these two things and starts messing around with them for his personal projects and starts getting involved with ZigCC. Soon enough, in June, Andrew Kelly creates ZigAR, and Mateusz integrates it into the toolchain proof of concept, polishes up the docs, and announces Bazel ZigCC on the mailing list essentially the same day. In a month or so, he puts up a work in progress diff or a pull request installing the Bazel ZigCC toolchain into our Go monorepo and building all of it using this toolchain. Obviously, there are thousands of failing targets, but it's still a starting point where you can point to and say hey, can we start iterating on this? Unfortunately, the team maintaining the Go monorepo still doesn't really have resources to pick it up, and at this point it's still not really that painful because it's inconvenient, but we don't really have some specific use case where we must have this. This is where actually we kind of the state we stay in for a while. So by the end of the year, we're in a situation where a hermetic toolchain would make quite a few use cases easier, but it isn't funded. Bazel ZigCC kind of works, but it's not production ready yet for multiple reasons. There are bugs, missing features, and incompatibilities with GCC in ZigCC. There are bugs, missing features in the Bazel ZigCC bit that glues the compiler in Bazel. The Zig issues aren't getting really prioritized by the Zig folks because they have more pressing matters to work on, like the Zig language itself, and there's no really realistic way that we can, invest serious resources at this point and implement, fix the bugs, and contribute them back. At the same time, the work in progress diff is still up there. Mateus occasionally bumps the version with new Zig releases, and that is where the story could have ended for us, and that is a story for where a story ends for a lot of such initiatives where it's not, decided up front, but just engineers trying to figure out a way of doing things in a better way. But fortunately for us, at the end of the year, in December, our team is tasked with evaluating ARM64 for Uber. This means that we will need to build our infrastructure components for ARM64, which means that we need a cross-compiler. And this is where things start falling into place. So this time we really do need a cross-compiler because our build fleet is x86 and x86 64, so it can't really natively build ARM code, and so at this point we still need to invest the work to actually make cross-compilation happen. And ZigCC is a strong candidate for the reasons I listed previously. We had a lot of internal discussions on whether it's a good long-term fit, and these may have ended because ZigCC does not have large users behind it, so it's risky. Luckily, the macOS compiler, cross-compiler won the argument here, and since this is a novel technology, we needed a way to de-risk bugs and missing features here. And as it happens, we had some budget left over, so we scrambled to arrange a support contract with the Zig Software Foundation. The contract we signed was very simple. It's essentially what it boils down to is we report issues to the Zig GitHub, ping the Zig Software Foundation. They hack and fix the features or bugs, and once done, they enter the number of hours worked. So essentially, we got a specific number of developer hours from them. With the support contract in hand and the decision to go ahead with ZigCC, real work can actually begin. So in January, we start paying back some of the technical debt that has accumulated over the years. There are multiple CGO targets linking to libraries on the host. There's even some code linking to precompiled object files, and these have to get fixed. Thankfully, this time we have the support of the Go monorepo team, and they take on this task. So we start reporting issues to Golang, Zig, and fixing Bazel ZigCC. And the goal of all of this is to have a green build of the monorepo using the hermetic toolchain with no significant performance regressions. In February, we partially integrate Bazel ZigCC and make it available under a --config flag, which essentially just translates to an extra toolchains thing. But this is really convenient because we don't need any additional patches to enable the hermetic toolchain, just to try building some targets. So this kind of really makes the feedback loop much quicker, where you don't have to apply some custom patches to make it work, and you don't have to work in a branch all the time. In April, first production artifacts actually built with ZigCC hit production. Our team owns the wrappers for building Debian packages in Bazel, so we were in a good spot to start experimenting there. We defined our targets using transitions, which means that Bazel build will do the right thing. It's no longer to accidentally build a Debian package containing binaries compiled from macOS, because previously, if you're just using plain rules PKG, if you don't specify the platform, it will just build for your host platform, which is probably not what you wanted most of the time. At the same time, we were actually migrating to a new CI system. And since these builds were hermetic now, we didn't really have to worry about what libraries and compilers are available on the build hosts, which was a very kind of nice thing to have. We also made some improvements to Basel ZXCC, making the usage of toolchains to target specific libc versions much easier. We can now specify a platform, and Basel ZXCC will link the targets against the specified libc version. So the first invocation here would link against libc 219, and the second would link against libc 231. So if you're running Jesse in production, you would probably want to compile all your code with the first invocation, because the second one might not, the binary, once you put it there, might not work. It might actually work, it might actually even work, but you'd better safe than sorry. So you want to use the correct libc version for your distribution. In June, we did a similar thing for Docker images built with Basel. We defined transitions and constraints to ensure that the correct version of glibc is linked against based on the base image, and this gives us more confidence in the images we build, removing a whole class of errors, and also offloading some responsibility from downstream systems where, like now, Basel has all the information to build the final artifact. It doesn't need, like, you don't need a separate place where you will store, like, okay, what platform do I need to build this with? When considering introducing a hermetic toolchain, we didn't even consider these specific use cases, and these were very nice to, really actually discover, because we weren't kind of like going for these, but they kind of just dropped out from a combination of things. In September, we finally had the full build pass. All the unhermetic dependencies have been replaced. This was a Herculean effort carried out by the monorepo team and Ken Miklas in particular. All the relevant known issues across ZXCC, Golang, our internal rules, and Basel ZXCC were fixed. So we flipped the switch to make Basel ZXCC the default toolchain. Unfortunately, we had to revert because we hit some unforeseen issues. We discovered additional use cases that we were not even aware of, where the toolchain was not performing well. Essentially, everything we were looking at looked good, but there were a lot of places where we didn't even know that we should be looking. And that's the state we're in right now. So we're working on ironing out these issues that we are discovering. The support contract still helps us prioritize the issues with the Zig if they're with Zig. And we think we're really close to enabling the hermetic toolchain across the board. I really wish that it would have ended with we have enabled the hermetic toolchain across the board, but it is what it is. And yeah, that's the story so far. I really hope that you took something useful away from this story, and thank you very much.